complex eigenbasis theorem. The purpose of the theorem is to solve a linear system of equations of this form. Here, A is a constant coefficient matrix, and it is real valued. So through the theorem, we want to give a formula to the general solution. So let's start with some assumptions of the linear system, and then we can arrive at a conclusion. So of course, assumption we have is that for the matrix A, we have only complex eigenvalues. And then that's why the theorem is called complex eigenbasis theorem. So some additional assumptions is that we suppose the size of the matrix N is an even number, N by N. So we represent even number as 2 times some integer, P, a positive integer, P. So, and A is a square matrix. A is an N by N square matrix. With real entries. So that's a very important information because it is a real valued matrix. Means each entry of the matrix A is real. So with that assumption, we can say that if, let's assume there is a set of linearly independent eigenvectors of the matrix A. Okay, so let's say if Vj, that's a notation for a vector, certain vector, Vj, it has a real part and has an imaginary part, I times the imaginary part. So here, J, 1 to P. These are linearly independent eigenvectors for A. Okay, so these are linearly independent. Well, this is a set of complex valued eigenvectors. So over the complex number set, independent eigenvectors of the matrix A corresponding to the eigenvalues eigenvalues, we use a notation lambda j because Vj is the eigenvector corresponding to the eigenvalue lambda j. So here lambda j is a complex valued eigenvalue. So here we have the real part denoted by aj, the imaginary part denoted by bj of this complex eigenvalue. So j is from 1 to p. from 1 to p. So, but you might be wondering, then you have p. P is only half of n. Remember, we assumed n as an even number, which is twice as this integer value p, right? N is 2p, but p is only half of n. We know we should, let's recall, this is just a remark that for A, which is a real valued matrix, and whenever you have a complex eigenvector corresponding to a certain eigenvalue, lambda, then the conjugate, let's take a conjugate of this. So we start with a v equals lambda v. If that is true, then the conjugate, both sides of the equation, is also true. And we also know that A is real valued. So conjugate of A is itself. So we can simply put a bar on here. So that shows that V bar is also an eigenvector corresponding to the eigenvalue lambda bar. Yeah, so we can, this one is simply same as lambda bar V bar. So you can see that V bar is also an eigenvector of A. Its corresponding eigenvalue is lambda bar. So that means whenever here lambda V is an eigenpair for the matrix A, then lambda bar V bar also eigenpair for the matrix A, the real valued matrix A. So because of that property, so we can see that whenever we have a complex eigenvalue, then its conjugate is also an eigenvalue. And whenever we have a vector as an eigenvector for A, then the conjugate vector is also an eigenvector. So because of that, then we can continue to say, then yeah, so that means although we list only p vectors, right? Although here in the statement, in the assumption of the theorem, you see only p eigenvectors, but actually we have 2p eigenvectors because their conjugate vectors are also eigenvectors. Although you only see as listed these p eigenvalues, j from 1 to p, so each lambda j is an eigenvalue, but actually there are additional eigenvalues. Those conjugate of those eigenvalues are also eigenvalues of the matrix. So just remember, for this matrix, we have 2p eigenvalues. We also have 2p eigenvectors. So although we don't need to list them all in this theorem, but you should keep in mind if I put include the conjugate, right? So they are also eigenvectors and eigenvalues. Okay. So now what when we continue, we want to say then from these independent eigenvectors, we have p, we can use the real part, imaginary part of the eigenvectors. Here, do you see that uj, right? uj, we see actually we have real and imaginary parts. For example, u1 will u1 w1 will be the real and imaginary part of v1 when j is 1. And U2, W2 will be the real imaginary part of V2. So because each eigenvector has its real and imaginary part, so we just list the real and imaginary part of each eigenvector here for the j from 1 to p. So let's, right, so that means we have real valued vectors now. See, U1, W1, they are real valued. U2, W2, real valued vectors. And then the last one will be UP, WP. And you realize yeah. So from each vector, we can get a pair of vectors. That is, it's from each vector, we can get a real part, imaginary part. That's a pair of vectors. So here, one pair, second pair, all the way to the piece pair. So we have two p vectors. So these two p vectors is a basis for Rn. Because they're independent, we can prove it. But yeah, so in this theorem, we'll list the result. This is a basis for Rn. That means for this 2p, n is 2p, remember? So our n is twice as p. So actually, you do see that we get 2p independent vectors, and they are real valued vectors, and they can be a basis for the space Rn. And not only these 2p vectors are linearly independent, real valued vectors as basis for Rn, also for any arbitrary vector C in Rn, the integral curve of the system x prime equals ax, that is the homogeneous system with constant coefficient a, satisfying the initial condition with satisfying the initial condition, that is when t is 0, this integral curve has a constant value c. That's the c. That's the initial data. So whatever c given, if our initial curve has that pass through the c, right? If x at t equals 0, will be with the value c. Then this integral curve, that means the initial value problem, has a solution, can be represented by a certain function. So we can represent this solution because it's a function of t. And okay, so let's write our solution x as this summation j from 1 to p, because for each j there's a component, and then We have P of them. So then we will add this up. So that's the solution. So we represent it as AJT. Remember the AJ is the real part of that complex eigenvalue. So here's AJ. You see AJ, BJ, right? Real imaginary part of a certain eigenvalue. So for each J, we have this E to the AJT. And then it is multiplied by cosine BJT. See, that's the BJ is the imaginary part of the eigenvalue. And then multiplied by a certain constant, Kj, Uj. Uj is a vector. Uj is the real part of the eigenvector. Hj, Wj. Wj is a vector. Wj is the imaginary part of the eigenvector, Vj. So have one part. So, but I still need one more part to show. So you can see, just recall what is the notation, the meaning. So Uj, Wj, you see, for the eigenvector Vj, we have real and imaginary part. So that is the real part, imaginary part of a certain eigenvector. Yeah, so as soon as we remember the meaning of the notations, then we can see how we can possibly use that information to represent our general solution, X. So our solution can be represented as, okay, there's another part, BJT. So HJ, which is the same as that HJ, you see HJ times UJ this time for this part. UJ minus KJ WJ. Okay, now we can see that this solution X, the solution X is represented as this kind. That's a typical term, right, for each J. For each J. When J is 1, it's e to the A1t cosine B1t. And you will use U1W1 and U1W1. Here you will have a K1 H1, right? H1 K1. So that is for each J you have such a component. So then when J is from 1 to P, you will sum them up, and then that's your solution. But then we want to add some additional condition because that is a representation formula for solution of this system, a solution of that linear system. So here, if we allow Kj, Hj are being arbitrary constants, and they will satisfy the system. However, we want to require Hj, Kj, those constants, to be such that the initial condition is met. So how do we make that true? Then we just simply impose, right? The Hj, Kj must be these constants such that, so let's where the real numbers kj, hj, um, um, yeah, should satisfy such values that this following must be true. That is when t is 0. So let's think of what happens. When t is 0, this is 0, right? E to 0 is 1. So that is 1. 1 times anything is just this, right? So when t is 0, the sine value is 0. It's all gone. So actually when t is 0, cosine 0 is 1. So all we left is this part. When t is 0, this we only have this. So let's quickly write it. That means just the kj, uj plus hj, wj, and it has to be when t is 0, what is the, remember? It has to be c. When t is 0, this should be c. That's the initial data. Yeah, so we have this initial condition. But don't forget the sigma. So j from 1 to p. So that must be true. C is the given initial data. So that means our solution is in this form, right? Sum of those exponential and this vector. And then the coefficients, those real numbers, hj, kj, must satisfy this system. Okay, in order to understand the theorem, let's work on a very specific problem. So let's look at a case such that the matrix A has complex eigenvalues. And so let's think of an example. Here's an example. And we're going to look at x squared equals a x. So I have a matrix A. Okay, so let me get matrix. Here I have this example, and x prime equals ax. And suppose we're going to suppose we have let's start with even a second order system. And maybe in reality you do not always have a first order. If you have a second order, suppose x1 is a displacement of an object, second order derivative with respect to t is negative 11x1 plus 6x2. And then there's a second object. So it's such a system. Suppose we have some spring attached to M1 and on a very smooth surface, and then attached with another spring and M2. Okay, so they can glide without friction, so just freely glide. So this is at the natural position. That means without stretching of the spring without compressing the spring, then that's the equilibrium position, right? The equilibrium position. So that is when x1 is 0, when x2 is 0. But if you pull, for example, the x2 to the right-hand side, then x2 will be positive because it's away from the equilibrium position. So we define a positive direction, a negative direction. If it's on the left side of this equilibrium position, then x will be negative. So yeah, so it's all relative to the equilibrium position. So our x1 means the position of the first object, m1. X2 is the position of the second object. So certainly they are function of time when during the motions. Suppose you start with the initial velocity and then they will change with time. So that these are the functions of time. And then when you have such a problem, you want to study the motion, that means the displacement function, you will get a system. So that's just to show you a possible system that we get from a physical phenomena. So here, suppose we have a system derived from this two-body problem. And it's a second-order system of two equations. And we know we can, let's assume, suppose the initial condition, the first object initially, that means when time is 0, it's at equilibrium. And the first object has an initial velocity 0. That means it was not moving, initially at the equilibrium position. So that's velocity position, right? So second object, we use the notation, we have already adopted notation x2 at 0, also at equilibrium position. However, it has a velocity, starting velocity. That's the derivative of the position function. The initial velocity is 1. So if we have if we're given this information, can we determine the x1, x2 for this system? Yeah, can we solve this using these conditions? So now we have a theory for the first order, so we can possibly reduce it, right, to the first order, because the second order equation can be reduced to 2 first order equations. The other second order equation can be reduced to 2 more. So we have 4 equations as a result. So let's do the reduction and then let's think what is the notation. So here the x1, we can still keep x1, and this x1 derivative, we have to name it, right, in order to reduce this. So in order to make a neat notation system, so actually we can just adopt a set of new names. So let's call x1 as z1. X1 derivative as z2. So let's just give us a new set of names. X1, let's use z1. X1 derivative, let's call it z2. That's the velocity of the first object. And then x2, we rename as z3. X2 velocity, x2's derivative is z4. So that is our new set of names. yeah, as you can see, this doesn't have to be renamed, right? It's just a different letter. But to make it nicely in this order, Z1, Z2, Z3, Z4, so we can see easily, we will get a system of 4 equations. So, okay, so let's write the first equation, okay, so immediately we can see Z1 derivative is equal to Z2. That's the relationship. Yeah, Z1 derivative is Z2. And Z2 derivative is this, right? Which is a negative 11 Z1 plus 6 Z3 with the new name. And then the first equation of the second order now reduced to 2 equations of first order. Now we move to the second equation of the second order. So here we continue to reduce. So using the new notations, we can see the Z3 derivative is Z4, right? Because of this, yeah. Z3, the first derivative is Z4. And Z4 derivative will be x to second derivative. Then we can see it will be negative 6 Z3 plus 6 Z1. So now we got a system of 4 equations and they are all first order. So we have a linear system with constant coefficient matrix. So let's look at two-body problem. Right, actually we know that this is the position of the first body, Z1 is position of the first body. Z2 is actually velocity of the first body. And Z2, yeah. So we know that Z1, Z2, Z3, Z4, they have different meanings, right? So just from this, we can see clearly from our rename process, we can see clearly that Z1 is the same as X1, which is displacement of the first object. Z2 is the velocity of the first object. Z3 is displacement of the second object. Z4 is the velocity of the second object. But anyway, so we know so as a result, if we get Z1 and Z4, I mean Z1, Z3, right, we will be able to get X1, X2 in the original second orders equation. So just to remember, in the original problem of second order, we have only X1, X2. Yeah, so we do have new variables, so additional variables in the linear system. Okay, now we are ready to look at this linear system just to write it in matrix form, so it's easier to see that Z1, Z2, Z3, Z4, and what's the matrix? So we can write Z1, Z2, Z3, Z4. And the matrix here, the first equation is the coefficient Z2, right? So it's a 0, 1, 0, 0. And in second equation, so we'll determine the second row of the matrix A, that is a negative 11, 0, 6, 0. And then Z4, that's the third equation. And then last equation is 6z1 negative 6z3 and 0 times z2, 0 times z4. Yeah, so we see this first order system of equations. And then we want to find eigenvalues, right? Eigenvalues of the system using linear algebra. So we want to find that is the determinant of this matrix A minus lambda I should be 0. That's the characteristic equation. So how do we find all the eigenvalues? So we just try to solve the system to find eigenvalues. Then we will find corresponding eigenvectors. So A minus lambda I, so if we see the above A, only the diagonal entry will be replaced with, each diagonal entry minus lambda. Okay, the second diagonal entry minus lambda. And the third diagonal entry minus lambda. And then one more. So next is keep the last row and 0 minus lambda. Yeah, so we see this is A minus lambda I, right? To make the determinant 0, then we can solve this equation for lambda. So solve this equation, if you remember the linear algebra, then you can do cofactor expansion. Yeah, you can choose a rule to solve cofactor expansion. So for this problem, we will be able to continue and then until you find eigenvalues and eigenvectors. So let's say if we have this result, let's go ahead, just use, if we have found some eigenvalues and eigenvectors, and then we can continue to representation of the system. So here is an eigenvalue. Yeah, it's a complex eigenvalue. It is a complex eigenvalue. And because of that, we know its conjugate also a complex eigenvalue. So let's, in the theorem, although it's not listed, in the other one is not listed, right? So we just keep in mind, here we have a complex eigenvalue, let's call it lambda 1. And another complex eigenvalue, let's call it square root of, we have square root 15i. Yeah, through calculation. For example, if we have this complex eigenvalue and the corresponding eigenvectors. So in order to make it organized, I want to show you a complete picture so you can see what we can do here. So lambda 1 square root of 2i, and it's v1, that is the corresponding eigenvector, is this 2. You can use MATLAB or some other tools to do the calculation, so you don't have to work manually to get the eigenvalue eigenvectors. So here, that's a complex eigenvector, right, for this complex eigenvalue. But you can write it to see better. So I will get the real part. Real part is this vector. Imaginary part is this vector. Yeah, so then you combine these two parts together, and the imaginary part times I add the real part, then you will get original vector. So that's so this way is just simply easily seen, like a real and imaginary part. You see, this imaginary part is also a real valued vector. That's this is a real valued vector. So we're going to use them. That's what we call U1, W1. Yeah. So we can simply remember the corresponding notations in the theorem. This is a V1, and it has real part, imaginary part, right? So that's the notation in the theorem. Okay, so there also a lambda 2. Lambda 2, let's lambda 2 is the square root of 15i. And its corresponding eigenvector, one of the eigenvectors is, because we know eigenvector is not unique, so but we just provide one eigenvector corresponding to this eigenvalue. So we can list, suppose we list this one. So other ones as multiple of this one, it doesn't matter which one you choose. So I will just, okay, here is a certain eigenvector corresponding to this eigenvalue, lambda 2. So again, you can write it as real part plus I times imaginary part. So real part is 3, 0, -2, 0. And imaginary part is 3 square root of 15 -2 square root of 15. So yeah, this is a way to rewrite the complex eigenvector, right? Write the complex eigenvector as the form, so you can see it's clearly complex. Yeah, with the real part plus I times the imaginary part. Yeah, so now we notice in the theorem it gave for a 4x4 matrix. In the theorem we get two. We provide two eigenvalues, right? Corresponding to the theorem here. So in this case, for our problem of A, matrix A as a 2x2, I mean 4x4, 4x4 matrix, here the n is 4, n is twice as p is 2. So remember in the theorem we have n is 2p, right? So in this example, n is 4 because the matrix is 4x4. But the p is just half of n. P is 2. So yeah, so that means we already get two eigenvalues and eigenvectors. But of course, the corresponding conjugate values are also eigenvalues and eigenvectors. So we're going to just remember that's all we need to remember. So although the theorem provided this, but remember that the conjugate value of this vector, right? So if I put a minus, that's the conjugate of this vector, is still an eigenvector. It corresponding to this eigenvalue, which is lambda bar. So actually we have 4 eigenvalues and 4 eigenvectors. Although 2 eigenvalues are listed, but their conjugates are also eigenvectors and eigenvalues. That's all. So the notation here is for the second eigenvalue, and this is the second eigenvector. So the notation U2W2 will represent the real part, imaginary part of the second eigenvector. Okay, so once we understand the notation in the theorem, then you see the reason we decompose, and then we're ready to use the theorem to give a solution. So here is the suppose I want to give solution Z. Okay, so let's write the Z as so that means we need to write the e to the a1t, right? E to the a1t. And then there's a cosine b1t. And remember, there's a k1 u1 plus h1 w1 plus sine b1t h1 u1 minus k1 w1. We'll have at least a part like this according to the theorem. So let's review the theorem quickly, because right now we try to make sense with the theorem, right? There, as long as we know the meaning, we know the conclusion, what can we do with the theorem? So if you look at the theorem, that theorem has a 1 here for the exponential function, the b1, right, for the cosine, and then k1 u1, h1 w1, so the sine. So all this, so that's what I was writing when j is 1. And again, when j is 2, right, because p is 2, when j is 2, we have some similar thing like this again. So we need to use U2W2, A2B2, all that information. So let's go ahead, continue. So when we still have, because the summation of when j is 2, we have A2. What is A2? Remember, A2 is the real part of the lambda 2 eigenvalue. Yeah. So we have cosine B2 K2 U2 plus H2 W2. So remember, U2 W2 are vectors. And then continue in this, for this bracket, sine B2 T H2 U2 K2 W2. So the structure is exactly the same. If you compare this part, right, with this part, that's the same. For each j, we have same construction. Then we add them up. That will be the solution for the system. So yeah, that's just to remark. Yeah, we have from 1 to 2. That's all we need for this. P is 2. So for this example, then we have a general solution. So if you want to put in the numbers, you see you have all the numbers. We already have the what is the A1, B1? Just go ahead, find the eigenvalue lambda 1. So yeah, lambda 1, see, that's the lambda 1. A1 must be 0 because the real part is 0. The B1 is the square root of 2. Okay, so that is done. And then the U1, we have it. So the U1 is this, right? W1 is this. So let's go ahead and put those values, and then you will see what it is like. So we can actually, with that form, then all we need is to substitute into the values. So the first is e to the a1. A1 is 0. So, and then basically this is 1, right? So we don't have to write it. So then we only have a cosine b1. b1 is the square root of 2 times k1. What is u1? u1 is that vector. And then h1, w1. w1 is the other vector. Oh, so I think yeah, so no, the u1 should be careful. We have to be correct. What is u1 and w1? So just to remember, yeah, so that is u1. That is w1. Yeah, so we can write u1 w1, and then that's all we need to do. You see, we have all the information to put our into the framework. Yes, so we have u1, w1, and then so this part plus some sine, right? Sine b1 times h1 u1, which is u1 is still same vector, but notice that h1 is in front of this. It's all from the derivation, so we have this form. It's not, yeah. Yeah, so for that reason, we have this form. h1 minus what? K1. K1 is the same K1 as that one. You see, same with K1. Times W1. W1, so it is 0, same. W1, I just simply copy the W1 we had already here. So yeah, so that is what? The thing I just wrote is just this portion. So we just did this portion, right? A1, B1, U1, W1, all in their places. And then continue. We cannot stop there. We still have to deal with the other eigenvalue and eigenvector. So let's continue with this portion, second one. So e to the a2. So yeah, it looks lengthy, but you see the structure. Once you practice, you will see continue, because e to the what? A2. A2 is also 0. Remember 0t. So that's a 1. So we don't need to write this. So we only write this e to the exponential function times whatever bracket cosine sine. So we have only that part. So cosine square root of 15t times K1. And this is, I mean, K2 now, K2. So that is U2. U2, remember, it's U2. Okay, H2. W2. W2 is okay, so you can double check U2, W2. Yeah, here is U2, here is W2. Yeah. So this A2 is 0, right? Because real part is 0. But imaginary part is square root of 15. So that's why we have A2, B2. Okay, so just continue. We have now cosine part, and then so we need to have the sine part, sine square root 15t times whatever here. So we need to, yeah, that's H2 minus A2, and here U2, W2 again. So we just copy the vectors U2, W2. Okay, so through this example, you see that, okay, we got a solution, almost, because you see the solution is integral curve, right? Integral curve, you see clearly it's, yeah, curve valued function of t, but still you do not know the k1, h1, k2, h2. They are not arbitrary. Remember, we imposed the one initial data. So what should be the values of h1, k1, h2, k2? So how can we choose these values in order to have that initial condition? So let's look at the initial condition. So this initial condition here means that Z1 when time is 0 should be 0, right? So we know this is a Z1, Z2, Z3, Z4. Yes, actually we know that Z1, Z2, Z3, Z4 will be respectively 0, 0, 0, 1. So that's our Z1, Z2, Z3, Z4 for the system of first order. And when time is 0, their respective values should be this. Yeah, all based on the given information. So we have this initial initial condition. So that's the initial condition for this problem, for the linear system. If that's the initial condition for the second order equations. At the beginning, we looked at second order equations. Okay, so now we are going to continue to decide. So here, we know that initial condition must be, okay, so let's choose a different color, must be 0, 0, 0, 1. That's the initial data. So that means this solution in this form, when t is 0, let's see, when t is 0, what happens? When t is 0, this is 1, right? When t is 0, that's a 0. This is all gone. So when t is 0, this part, that's the only part that's remaining. When t is 0, this is 1. This is remaining. And the sine part is gone. Sine t is 0, 0 times anything, 0. So let's only take care of this, and that add together should be initial value. Okay, so we're going to have K1H1, K2H2. So that means we have K1 H1 K2 H2 to satisfy that initial condition. So let's make it equal to this initial, satisfy this initial condition, so that the Z1, Z2, Z3, Z4 will be 0, 0, 0, 1 respectively. So that is how we can choose K1, H1, K2, H2. All these K H values are real numbers. So then you can see that's just you solve a linear system, then that's all you need to do. So this system is the same as, let's write this in a linear system. It's K1, K2, K1, H1, K2, H2 will satisfy this system with first column of the matrix being that vector, second column being, and third column, fourth column. Yeah, so you notice what are these columns, right? So this first column here is the U1, that's the W1, that's the U2, that's the W2. So here when P is 2, and we get a 4x4 matrix, and then we can determine the 4 real values. Yeah, for the values of those variables to make them satisfy the initial condition. So once we solve this, and we will get this, that's the weights for the our solution of the initial value problem. So you see, it's a process. It's a process, and understanding the complex eigenbasis theorem, and then you apply it to a specific problem. Of course, applying to a specific problem will help you understand the theorem. So, and you see this example of two eigenvalues and their eigenvectors. In fact, actually 4, right? Because their conjugates are not mentioned. But it doesn't hurt. We don't lose anything, because even if you consider the conjugate, see what happens if you use the conjugate, right? Instead of the plus, we put a minus. Consider the conjugate. Then what? The only thing that differs is the sign. So instead of W1, you will have a negative W1, negative W1. So then you do the, if a solution is complex valued, then we know that it's a real part and complex, and the imaginary part will still be a solution of. Then you eventually you generate the same side. So we didn't lose anything when we do not use the conjugate. So the solution set, the general form is still a complete form. That means we do not need to use the conjugate. We already have the complex form. So we just give a general representation. So through using P, right, for general P number for eigenvalue eigenvectors instead of 2P number of eigenvalue eigenvectors if you have a matrix 2P by 2P. So this is a theorem together with illustration.